Morning. Welcome to the second day of NetBSD Con 2008. Our first talk this morning is from Kristaps Džonsons.
I'll say it.
You say it later. He's going to talk about logical isolation in the NetBSD kernel. Kristaps is a NetBSD committer, I believe. No, he's not. I screwed up his intro now. And has prepared this paper for us. And so nice to see everyone awake at 10 o'clock. We'll see if you're all awake at 11. So now you can pronounce your name correctly. There's a one of these.
As mentioned, my name is Kristaps, and the topic of the conversation is logical isolation in the NetBSD kernel. I assume that while talking, people are going to drift in, maybe not, I don't know. So we have a decision right now. We can begin with a demo or end with the demo, or we can begin with the demo and end with the demo. So what is there to think? Do you want to see something fun now or later? So a little bit now, a little bit later. All right. So the demo might be a little bit nonsensical to those of you who don't know what molt is. So I'll begin with a very, very brief introduction. But basically, the system I'm about to talk about is called molt. It's been under development for a few months now, 3, 4, 5, 6 months, something like that. I'm not sure. And what it basically does is it takes the user land and pluralizes it, so that there are multiple user lands within a single host. And within those user lands, the other user lands are completely invisible. They can't be seen, so one thinks that one's running in one's own environment. And it's all implemented in the NetBSD kernel, specifically the NetBSD 3.1 kernel for now. So let's jump right into a little demo right here. So what we have right here, can everybody see this? More or less. I'll try to actually talk about what's going on. So this is actually a live demo right now, very, very live. So I'm a little bit nervous that while doing it, we're going to get some ugly panics. I hope that doesn't happen. It hasn't happened yet. But I know there's a nasty bug in there somewhere that the current version is fixed. So I'm going to really hope we don't hit it, because that would be very embarrassing. And I'd cry. So nobody wants to see that. So this box right here that I'm logged into is very far away. It's actually in Riga, Latvia, in BSD.LD. And what it is it's running NetBSD 4.0 with Xen in it as the DOM0. So this is NetBSD 4 Xen. And let's show a new name on that. So here we have NetBSD, Xen BSD LD 4.0, NetBSD 4.0 with Xen 3 DOM0 kernel config. And yes? I can't, unfortunately. That's why I'm going to say it while I'm talking. There's really not that much to see. And if it panics, I'm going to keep on talking as if nothing happened and hope that nobody can see it from where you are. Of course, that won't happen. So we'll see. Anyway, so yeah, so here we have a simple NetBSD Xen system. And what I have is a bunch of pre-prepared images, and I'll talk more in depth at the second demo, assuming we get that far. About what they're doing and how I set them up. So here I'm going to create basically an installed molt system and boot into it. And this is going to have 2 disks, and what I'm going to do is actually show you the system working as it would boot and everything. So what's booting right now is a NetBSD 3.1 para-virtualized system within Xen. So the guest is NetBSD 3.1, so the kernel has been modified for molt. And it's running in para-virtualized molt mode. All of that worked out of the box. I didn't need to change anything because molt is implemented in the very top half of the kernel, not down in the guts of it. All right. So here I have, in case you can't see, I logged into NetBSD 3.1, and the kernel config file is very similar to the Xen 3 DOM-U file. And so that means that it's running in para-virtualized mode very nicely. This looks like a regular system. I mean, if I run PS and everything, I see everything that a normal system would have. I have init and sendmail and cron and all that stuff. But you'll notice, maybe, if you can see this, that something is missing. So here I ran PS AX, and it started with process 1. What does PS AX usually start with? Or what does it show?
The kernel process.
Yeah, there are no kernel processes. So as you can see, I cannot see anything that's in my kernel right now. All the kernel threads are hidden from me. And the reason for that is because all the kernel threads are running inside of a different Molt instance. So they're invisible to me. I can, however, show them by using a special command that I wrote called instps, which is now going to show instance 0 all of the kernel threads that are running. There's a scheduler, crypto, event. I don't actually know what a lot of these do, but they're all in there. So I just now peeked into a different instance, and there I have the page daemon, something called the inst daemon, which I wrote, the asynchronous I/O daemon and everything. All of those are in a different instance. So now I'm actually going to start one and hope that it doesn't crash. Instances basically live in entirely separate devices for now for hard drives. Networks doesn't appropriate it. So, what's the name of the Zen piece? NetBSD1A. So now I'm going to create an instance that boots off of the XBD1A device and look into it. So here I just booted another instance, and here it shows if anybody recognizes VFS mount root. This is VFS mount int root, which is doing something very similar. So it just went through all the file systems, booted off this other disk, and somewhere on the machine where I can't see, we have now a fully separate instance running. It's got syslog in there, SSH, inetd, and cron. So I can't see it at all. However, for the purpose of this demonstration, I can log into it. So now I'm going to SSH into the local host. I'm not running SSH right now, the other one is, the other instance. So if we look at host name, right now this is netbsd 31.bsdlb. I'm going to SSH into myself. And I'm running netbsd guest.bsdlb. So now I'm in a fully separate instance on the same machine. And it's got its own processes, its own mount list. As you can see, when I run mount in here, well, you can't see it, so I'll read it to you. When I run mount, I have dev xbd1a, it's the root device. When I exit out of this SSH and run mount, the root device is dev xbd0a. So they're fully different. They've got different mount lists. I can't see any of the processes between them. And so this is an example of two fully separate instances that are completely isolated from one another, running inside of a single Zen instance on NetBSD. So we kind of have a tool tier of multiplicity. We have Zen running with multiple Zen instances, and then within one of those Zen instances, I have a Molt running, and Molt has multiple instances running inside of it. So that's the demo. Now I'm going to actually talk about what Molt is, because there are, I think many of you have absolutely no idea what I just talked about. So I'm going to do the same thing at the end with a little bit more in-depth. If anybody can quickly remember the A-term or X-term font codes so that I can start on the next term with a larger font, let me know, because I don't want to spend the time to do it. It's not for the presentation. You're going to have to pretend at the end you didn't see that. So erase it from your minds, and we'll start afresh. So, good morning. Or this is logical isolation of the NetBSD kernel. I assume that everybody knows what NetBSD is. I assume everybody knows what a kernel is. The term logical isolation I'm going to explain during the course of this. My name is Kristaps Džonsons. I work at the Swedish Royal Institute of Technology's Center for Parallel Computing. That would be in Sweden, in Stockholm. What is this all about? I'm going to introduce what Molt is. Molt is the system that does the logical isolation, and talk about what it does and how. What I'm not going to do is talk about things like administration. I assume that everybody can figure that out later. And I don't want to mess up the whole thing talking about that. I'm also not going to talk very much about why I did this, because it's a little bit tangential and we'd be here forever. So I'm going to begin with some terminology. It might be a little bit boring, so I tried to have as many pictures as possible. everybody recognizes this, right? It's the shell. I'm going to use this picture throughout this whole presentation right now to talk about our user environment. Our user environment is pretty much everything that's going on in the system as we know it, in a standard system. We have the init process that's running off of the console. It has WD0A is going to be the root device it's running off of. It has a file system. There are a couple of processes that are running Getty. They also have devices, GTY1, GTY2. There's a user that's also running under all this root. Let's say I'm logged into it. I have a shell running. So I have standard in, standard out, and standard error. I have another user. So all this stuff, when you put it together, kind of constitutes the user environment running off of resources that are provided by the kernel. So when I say the word operating instance, what I mean is the userland context. I say the userland context because on a general system, there's only one. We start up the computer, and everything we have is right in front of us. We can all access it. It's visible. Everything is right there. So that includes all the users, including the superuser root, all open files, all processes, all network things, network connections, network devices, available devices, mounted file systems, K events, K nodes, accounting, all that stuff is our user environment. It's all available to us in the kernel. Formally, I call an operating instance a collection of tasks or processes that's mapped to a shared set of resources in the kernel. So meaning that's the stuff that we can access. And an operating instance is defined by the fact that other tasks can see the same resources. I should explain, by the way, that I work very, very much in math. So a lot of my explanations sound like that, because that's generally how I think about things. It's not very practical. This is my job. I'll try not to mention it very much. So in terms of pictures, that single operating instance that we have maps through kernel services into physical devices. So everything that we see from here is in the kernel. So there's a very clear distinction between the userland and the kernel, obviously. And the kernel is the kernel with the operating instance is the operating system, but they can be divided. Malta is going to do something pretty fancy, as we'll see later. So how it is that conventionally in operating instances is our full operating environment. It's everything we know. And being mostly computer people, it's everything that we love, or in some cases, it's everything that we hate. Also, for most of us, it depends on what hour of the day is, because it's morning right now. You can all guess which side of that is. So let's be a little crazy, right? What if we could take this whole operating instance and have many of them? It seems possible, right? Because we're already out of the kernel. So let's talk about the possibility of having many of these. This is called multiplicity. We can do all sorts of crazy things. We can do virtual hosting. We can have completely separate user environments, each one having their own SSHD, each one having their own web server, SendMail server, mailman. All that stuff can be put into an instance and basically separated from other ones. So instead of having many, many users all in one system, we can have each user having their own system and being root, basically. More something that I like, we can have isolated high-performance computing job scheduling. So if we have a cluster of machines and we have thousands of potential users, the demand for the machine is going to outstrip the supply. We need to have a very, very smart way of scheduling things. And we can do that with something like this, because we have fully isolated environments, and we can schedule them to run just like we schedule processes to run. Test installation, that's an easy one. We can see exactly what's happening, so we can start with a fresh install our system, and see what kind of bogus garbage it throws everywhere. We can isolate corrupted binaries. So it's all those Linux binaries you have running on Compass. You can kind of keep them nice and contained, not like right now where everybody can see everybody else. So there are lots of options for this. But what it comes down to is one single machine, one single operating instance and kernel divided into multiple operating instances over a single kernel. It's kind of I say this is a plural operating instances, or I pluralize the operating system. This is the kernel. So many of these are over one single kernel. And I say that over and over and over again because it's kind of the today of the entire thing. I call this multiplicity. And multiplicity means many operating instances running inside of a single kernel. And they're all isolated from one another. It's very important. An isolated plurality of operating instances, as just said. And the resources, which again is what I think about most of the time, if we look at it mathematically, then the resources can be non-overlapping. So the range that is seen from a particular instance is non-overlapping the resource code. And isolation, of course, means that that tree of processes that's in one operating instance can in no way inflict itself on the other. And I mean absolutely no way. So we can't do funny things like, I'm user 1 in this instance, and there's another user 1 in another instance. Now if I change my limits, then will that affect the other one? If I change my quota, because a user is just a number, right? User ID 1. Well, the kernel has to somehow know that there's this user ID number 1 and that one. Now that seems pretty easy for like a regular user, but a super user also has to be that fully conflict free. So the super user of one operating instance cannot in any way inflict itself on the super user from another operating instance. This is down to things like the network card has to be fully different. I can in no way inflict myself into the other network card, except by means, of course, of logging into it as if it were a different system. So we want to take the illusion that there are multiple computers and preserve that and have it always be maintained. That's the whole point. If there's ever a moment when isolation is not observed, everything kind of falls apart. For example, let's say there's through Compat Linux, we can change the host name. And I have not somehow thought about this in my isolation mechanism. So I can change the host name for multiple instances. Well, then there are no longer multiple instances of the same one, because they can access that one single shared value. And this sounds pretty familiar, right? There's like a whole party of people who do just this. We just saw yesterday the thing about Chaos Jail, which does something like this. FreeBSD Jail is probably best known for doing instances. I think all of you know about FreeBSD Jail. Or should, because it's pretty useful. So there are zones actually do something very, very similar. There's Linux vServer and OpenBZ and all sorts of, don't say the words, I'm not supposed to. But Linux has all sorts of stuff. I'm really not going to concentrate on that. Zen is another one, but Zen I'm not going to talk about because Zen does not pluralize operating instances, it pluralizes kernels. vkernel for Dragonfly BSD also does operating systems. Kimu and all these other systems also do that. We're not going to concentrate on that for now, so let's just brush that under the rug for now. We're concentrating on operating instances, not operating systems. And last but not least, kind of the new member of the party is Malt. So all of these systems, of course, provide more or less operating instance multiplicity, or do they? When I wrote this was last night, it was very funny. And obviously it's not funny anymore. So it was supposed to be evil, or do they? People were supposed to go, thank you. Right, so or do they? If we say that operating instance multiplicity is full isolation, and you have one single area of non-isolation, as a mathematician, I would say that that whole house of cards falls down. We can't say it is anymore. Of course, some people like FreeBSD continue to say that their system is providing multiplicity. I will make sure. So let's talk about Malta. It's not about FreeBSD, it's about NetBSD. By the way, this image is courtesy of one young man at the Stack Computer Club. I may be trampling on all sorts of copyright, so beat me later if that's the case. I apologize. It looked nice. I like the whole cards reference. It's not a house of cards. NetBSD 3.1 is what I based this on. It's technically 4 for now. Why I did that is not really all that exciting. It just happened to be something that isn't changing, that's relatively new, that was clean enough, and I just used it. And we'll talk more about that later. So what is Malt? Let's talk very specifically about this. It's yet another operating instance multiplicity system. But the strategy that I use to have this operating instance multiplicity is what is important. It's implemented as a fork of NetBSD 3.1. It's a big fork, as we'll see later. There are a lot of changes. And it lives at malt.bsd.lb, which I think hasn't been updated in a week or two. but that's where it's known as. So what sets Molt apart from the others? You know, what makes it special in this party of FreeBSD jail and Linux and all that stuff? And what sets us apart is the strategy that we use to actually have this isolation invariant. So in order to explain this, the whole basis of Molt, why it exists, let's talk about conflict areas again. We talked about a host name earlier, being able to read and write from a single host name value for multiple instances. Well, you're out of luck at that point. You're no longer isolated. So what I say is that if there is an overlap between instances, then we break isolation. And how conflict areas are handled are called the strategy of the operating instance multiplicity system. Molt strategy is specifically designed so that it can prove isolation, not just pretend it's there with clever hand waving at conferences. I want to actually be able to show that this system is fully isolated, both mathematically and practically speaking. So I want to have a system that says, you're isolated. Good job. That's the whole intent of Molt, that we can really say that it does what it does and prove that it does what it does. So I'm going to jump right into a code example. I assume that maybe you can see this, maybe you can't. This is from FreeBSD Kernel. And what it is the system called getPGID. What exactly that does doesn't really matter right now. But what's important is that this is a system called the content. And here I want to extract value that has to do with processes. Now, inside of FreeBSD, this is references jail, right? I have a function p can c. And basically what's happening in there is first, I look up the process. So I'm process 1, and I want to see the process ID of process 2. Now, if we are in multiple operating instances, I should not be able to see the process number 2. It should be invisible from me. So in FreeBSD, we manually have to say, am I allowed to see process 2? So this is what's called a conflict point, because this is an area where two operating instances could have a conflict. If one operating instance says, I can see process 2 is in another operating instance, then I've broken isolation. So this is the area where that magic actually occurs in FreeBSD. There's a function call that says, are you, can I see you? No? Yes. That's just how they do it. Now, I'm not going to talk about this that much right now. So let's talk really quickly about what Molt does. In the same system call, sys getPGID, in NetBSD 3.1, you can see these sources. They're available online if you're really interested. When I actually look up the process, I pass in this value, p_int. Now that is a structure that identifies the instance. So that kind of has my context in it. When I look up the other process, I'm going to be looking at a process table that is local to my own instance. So instead of saying, can I see you? A priori, I can see you because the table that I'm looking you up in is in my instance. So I cannot see your table of processes. It's a physically separate piece of memory. It's a data structure that's inside of the context instead of being global. So we're going to talk more about what that means, because again, it's central to what Molt is, and why, in my opinion, it's better than the existing strategies. So if we take FreeBSD jail, or Linux vServer, which is the same thing, most of them actually do this. Conflict areas are individually resolved at each point of conflict. So every time we have a potential overlap between instances, at that point we say, can I do this? This is what I call functional isolation, because the actual isolation occurs in runtime. Every single time I encounter that, I have to do a manual check. So every single point of conflict has to be resolved. Kernels are big. It's a lot of potential areas. And we'll get into the exact parts of it a little bit later. Molt, on the other hand, what it does is instead of having the resources be global and access to them be border checked, the actual resources are drawn into contexts. And you can only get into your own context. So they're always separated from the start. And I call this logical isolation, because it's logical versus being functional. So if we look at this in terms of a picture, if this is these are separate contexts. So this could be like a task inside of a context. This is the kernel barrier. This is in the kernel. These are resources like the process table. Now, if I have 3 context look up process number 3, they're going to go to the same area of the process table. So that actual place in the code where I look up a process in the process table in FreeBSD jail has to be specifically addressed. So that conflict area needs to be found, routed out, and I need to add that prison protection code around it. So every single area of possible contention needs to be found in the kernel. Every single system call coming in has to be carefully examined and looked for and isolation approved. So specifically, we have 2 contexts that are going to map to the same area when I do something like kill to process 1. Because process 1 on one instance, when I have the same process table, is going to go into the same part of the process table that's shared. So again, I have to do this p can't signal right there, where I make sure that I'm allowed to touch it. Now, something like molds, what I do is, if we're looking at these as being resources, resources are usually owned by something. The process table is global, so what I do is I take the process table and I dump it into a structure that has context. When a request goes into the kernel, that context is associated with my credentials, so that I can actually say, here are my credentials, get my context, get the process table from the context. Now another process, in a different instance, is going to do the same thing, but they have a different context. So there's never any overlap. I don't need to check for overlap, because already things are separated. They're already isolated. And again, this is logical isolation because the actual enclosure of the data is brought into contexts. And again, in terms of the kill signal right here, where I actually find the process, I'm doing this off of my credentials. So it makes it a lot easier. Instead of having to go to every single location of where a process is looking up another process and having that can signal, I already know that I don't have to check, because there are multiple process tables. There's not just one. It's not shared. Logical isolation is very nice. It can be proven. I can look at all of the data in the kernel, global data, and say, is this shared by multiple people or is it not? Things like a pool of memory, I don't really care. It can be global because it has no context attached to it. Something like the process table needs to be brought into the context. It's called appropriation. New code that's written in the kernel inherits from the existing mechanism. If I add new code that does something like something really stupid. Let's say I want to add a particular limit to every process that I can see. So I want to change the nice value of every process in the system. I don't need to worry about doing that PR can see for every single time I'm talking to a different process, because I know that I can only see the processes that are in my context because the process table is in my context. Process table for other contexts is completely somewhere else. I can't get to it. The nice thing that I like is that it's top-down instead of bottom-up. So instead of attaching the leaf of the problem tree, I attach the root of it. There are several cons. There's a lot of code churn. If you look at the initial check-in for FreeBSD jail, there are a lot of files that are affected, but they're very, very small changes. Usually just that enforcement mechanism of, can I see you, can I not? Molt, on the other hand, as we'll see, has a lot of changes. And it has a lot of code churn, a lot of complexity. But as you can see just by numbers, pros outweigh the cons. It's completely defensible. And there's also a little bit of memory and time overhead. Whenever I start an instance, I have to have 2 process tables. If the process table is 4 kilobytes, then I have 2 4-kilobyte segments. This can be optimized away to a certain extent, but the fact remains that every instance has its own data structures inside of the context. So I am, in effect, duplicating a lot of that. It's kind of a necessary evil. I'm just not convinced. Very good answers. Okay, so let's talk a little bit more about Molt in terms of its practical implementation right now. Again, I said built from a fourth NetBSD 3.1 system. Thus far, there are about 600 files that have been changed. 8,300 lines of insertions and 5,600 lines of deletions. So it's pretty big. This is actually probably going to get scaled down in the end. I think I took this measurement when I was trying to appropriate BFS. which turned out to be a disaster, complete disaster. As I found out, manually appropriating VFS when you have 400 functions to change just doesn't work. And we'll talk a little bit more about that later. But it's a big change. It's not small. It's not like FreeBSD. There are a lot of systems that have changed, and it changes all across the board too. Changes for the better. Struct prison is kind of the basis of FreeBSD jail, and in fact, we actually put struct inst in the same place, and I think that hangs off of struct ucred. So every ucred has an instance that's associated with it. And here's just a kind of an abridged version of it. We have things like its unique identifier, a referent count, parent instance, I don't know whatever that gets, logs, host names. This is all, for the most part, global data. And then here, I have anonymous pointers that are file local scoped. But the actual struct inst contains the stuff. So our process table is somewhere in here. Everything is in here that we might possibly want to get at. There is no more global data in terms of there is some global data, but the context-specific data has all been appropriated into this one big structure. So when we break the structure down, there are basically two parts of it. There's public members and private members. Public members can be seen by everybody in the system. They're just sitting right there in the structure, waiting to be massaged and enjoyed and loved and cared for. Private members are declared as anonymous pointers inside H file, and those are defined with file local scope. KLM is the same thing. It's just very easy because I don't need to worry about the actual process table sitting there in struct inst, making every single inst.h, including file, also have to include proc.h and all that stuff. So this actual data type, inst account T, is type def to a pointer to a structure that is actually defined in a file local scope elsewhere. That makes things nice and handy, keeps them contained. Fortunately, the kernel already does that, so I'm just inheriting from the kernel spectrum. The actual process of starting an instance, and we saw that in the very beginning. This represents the new way of doing it. There's also an old way, which was a little bit more broken. But instcontrol is a new system call that I introduced, and that has all the control of instances. The rest of it is up to syscontrol. When one runs instcontrol to start an instance, basically it forks the kernel thread. The kernel thread then subsequently forks an init process, which is like init. It's basically a stripped down init, because I don't want to do things like getting and all that stuff for now. Inside of the new instance framework, so the actual instance structure is created at that point in time with the new process. It runs, it sleeps, so everything happens, all that magic goes on. And then when everything has been reclaimed, so when all the resources go down to zero, all network sockets have been released, all files are closed, all processes have exited, then the system goes away. So everything is reclaimed, all the memory is free, that kernel thread exits, and everything is back to normal. So you can start an instance and throw it away very, very quickly. Very, very, very sub-second, so really quick. One last note on resources. I mentioned earlier that the kernel structures are appropriated into a system, but that really doesn't reflect on the real world in terms of devices. Devices being probably the most important part of your computing experience. So what I do is I talk about owned resources and assigned resources. An owned resource is something that is implicitly part of your context, like hostname. An assigned resource is something that's given to you by the administrator, like a disk, or a floppy drive, or a mouse, or something like that. So an owned instance, an owned resource is already in struct inst. An assigned one is something that has to be done by an administrator. And we'll talk a little bit more, maybe, about that. But that's important in that there's a little bit more administrator intervention that has to occur with this particular system. Because if I have two instances, they each need to have a different disk. I have to tell the instance it's allowed to see this disk, and then tell the other instance that it can see another disk. So that has to occur manually to a certain extent. The status of mode, it exists. It's a real thing. It's out there, as we saw, it was just running earlier in the demo. It's not production stable, it's a work in progress. So don't actually use mode for anything important. The current port that I have that's off of NetBSD 3.1, this is why Bolt has always said that it's NetBSD 3.1. Because if you port it to other systems, it's an idea. It's a prototype implementation. It's just a way of taking these ideas and giving them substance. The system may be used for testing, and in fact, I use it very, very commonly. Malt is developed in Malt. Sorry about that. In terms of what's actually been done, the framework is already in place. Obviously, that struct instance is very well filled out. Many, but not all, own resources have already been appropriated. The process table, the user hash table, sockets, k-events, k-nodes, system plate, VIPC, all that stuff has already been pulled into instances. A lot of things, of course, remain, but a lot of it has already been done. The assigned instances, the assigned resources, basically devices, for now must be manually put in by the administrator. So your /dev tree has to be manually pruned. The network also is fully unappropriated, so it's completely flat into its address space. And again, this is only because it's been under development for a few months. It's not very old, it's a young project. But there's very, very active development. Things happen all the time with this. If you look at the history of development, in terms of the website, you'll see that things happen all the time. This is my job, basically, so a lot of things are happening. I actually anticipate a fairly stable system in the next few months. That's a very realistic goal, I think, because it has very concrete implementation goals on what I want to have. But basically, I want all of PSTLD. There are like 10 subdomains, I think. All be put under instances. And that includes things like CDS Web, HTTP, Postfix, SSHD, whatever people are running on there. Once this works in a stable, then we can begin to consider the future of it. Properly implementing Malt, for example, on a real, more modern system like NetBSD 4, or Current, or whatever, or OpenBSD. The system is very easily portable from, it's just an idea, as mentioned earlier. The actual writing of Malt right now is manual, but I'm working on some voodoo magic that will allow me to automatically do the stuff that I'm very painfully manually doing right now, like appropriation. If I want to appropriate, say, process tables, well, there's a lot of other dependencies in there. It's not just process tables. It's the counters that are in the process table. It's the current references, maximum values, all that stuff needs to be appropriated along with it. I don't like doing that on my own because it's hard. It takes time. Sitting there with C-scope and figuring out what every single variable is and whether it should be appropriated or not. I don't have a tool that does it for me. And it's I think there's a reasonable request, and that research is underway right now. In terms of technical goals, that tool I just talked about is called Malt Toolchain. And there are going to be a series of tools that do this for me, that both verify the isolation mechanism and also do the actual isolation itself. I want to have the full appropriation of soft resources, or as full as I can get, pretty much. That's kind of hard to do without the tool, because I could always be missing somewhere an integer that breaks invariance that I just don't know about, because it's not in the top of the kernel file, it's somewhere in the middle. And there are a lot of places that do this. What's a good example of that? The hooks file. It's in one of the kernel utilities. Has global values in the actual source file, like down in the middle and at the bottom. I only found that later, and I was like, oh, that breaks everything. So I wouldn't have seen it because it's not on the top, and I usually expect variables to be at the top of the file. So things like that, when doing it manually, cause significant problems. Another technical goal is assigned resources. So I need to be able to broker things like hard disks, CD-ROMs, that sort of thing, with an intelligent permission model. We talked a lot about invariancy between instances. Well, how does that work with administration? There can't be like a root, because what does that mean in terms of Malt? With FreeBSD jail, they have the tag phrase, confining the omnipotent root, right? Is that correct? Something like that? But it doesn't, does it? I mean, that's a total non sequitur, because there still is root in the root instance, in the host, and he can still do everything. So it's a lie. Don't drink the Kool-Aid. We run into that problem right now, where how do I do that? There can't be a root instance because there's no hierarchy. There's no notion of hosts and guests. It's all egalitarian. So one thing that's under development is a very, very nice permission model that just uses what instance are you coming from? You're allowed to do this. You're allowed to do that. I think it's fairly straightforward. It just needs a MAC or a role-based access control to be plugged into there. But that's nothing terribly technical, it just needs to be done. That's the access module. So that also will define the inter-instance message passing, where we have something like the InstPS utility that I showed you earlier, I'll show you again. Who gets to use that? Who doesn't? You know, who gets to see into which instance of that? All that has to be defined. So what can you do? I have to do my, have you seen the Uncle Sam poster? I want you. What can you do? Just use the system, you know, play with it. I need core dumps really badly. I need panics. The person who's testing it right now just takes pictures of them, screenshots of BG. It's very helpful because that usually shows me me being an idiot over and over and over again doing no interview references. But other reports we need for documentation, for the website media, for kernel sources. There are a few user-led sources. There's bootstrap scripts. All that stuff can have errors, and I want to know about all of those errors. Then you can send me those errors at kristaps@domain kth.se. There's actually a full system for bootstrapping a molt. It's called molt bootstrap. And it's 2 scripts that both install the kernel after configuring it and compiling it for you, and also installing all of the user-led sources, which requires libc to be recompiled because of the new system call. But it's all done for you. So all that work has been done. And so 2 scripts, very easy. I very regularly run molt inside of virtualization because I want to see when it crashes, obviously. So I'm very familiar with running Zen and molt using virtualized molt in NetBSD 3.1. I ran it a lot under Linux KVM. People have run under Parallels in VMware. It works. It also runs on real hardware, but it's not as useful. That's it. Thank you very much. I'm here because of the Baltic Grid, and KTH, and of course BSD LB, and specifically Michael Dexter there. Was a lot of help and pushing and lots of bug reports and so on. Thank you very much. The demo again, we can pretend we didn't see the first one, if anybody would like to see it. So now it might make a little bit more sense about exactly what we're looking at there. So again, let's actually log out of this. You're not seeing this right now. You're not allowed to see the programs. Oh, who was researching fonts?
Just to regulate external.
Yeah, sure.
Just control and press control key. Right click.
Oh,
No, right click.
Yeah, and go down.
no, I don't have it.
But
What I can do is, this, right? Excellent cell, yes. I just want big.
I think it's very big.
Everybody see that? Excellent, but I don't want it to smash.
I guess you want the family of.
I thought you were Unix, like everybody here is a Unix wizard, right? Yeah, what's going on here? Oh, you don't know. I'm frankly shocked here.
No, always on the.
Ah, there we go. All right. Let's select it. And I believe FN is the font. Hey. Sorry for being old and using FEW. I don't know any other way. I've always wanted to switch to KB. It's not worth it? All right. Please don't try to blood break into this. Oh yeah, this is an honor. That was Michael Dexter doing that, by the way, so I have nothing to do with that. Right. User shut down the existing one. Let's see here. Yeah. This is making the existing motor electronic die. So can everybody see this, more or less? Yes. More, I think, rather than less. All right. So again, here I'm in the Zen NetBSD 4.0. It's very handy, by the way. Nobody's played with it. It works very nicely. I haven't had any major issues. Sometimes I have issues in jumping into the console once it's already started. We're going to have a pair of virtualized guests. This particular machine does not have Intel VT or AMD HVM or whatever the virtualization, in-processor virtualization is not run on this. Those all pair virtualized. No, the steps that went up to this, I think I'm going to go over. So beside the actual NetBSD 4 Zen installation that we have here, I had to install Molt, obviously. So what I first did is I downloaded the CD, image of NetBSD 3.1, downloaded the kernel, booted into the original one, did an actual installation of NetBSD inside of that instance, exited out of it, froze it, copied it into 2 disks, logged into one, and ran the Molt bootstrap code. So basically downloaded the Molt bootstrap package, ran the Molt bootstrap script, rebooted into the new kernel, then ran the Molt installer, which does the actual userland tools, and all set. So that just happened before, just last night actually, so it doesn't take very long, depending on the speed of the network connection. So now I'm going to start the Zen instance for NetBSD Molt. This is just a standard user map for the most part of NetBSD. So very, very few changes here. So what do we have? As we can see, I'm running off of the Molt Zen3 DOM-U kernel configuration, which is just the exact same thing as the Zen3 DOM-U. As you can see, I did compile it last night fairly late. That's not something I did a long time ago. I cooked up. Right. And again, the strange thing immediately to notice is that we have no kernel threads, as we pointed out the first time. So this is the standard NetBSD user land with a Molt kernel for NetBSD, and somehow all the kernel threads have gone away. And of course, the reason for that is because the kernel threads are in a different instance, which is kind of conventionally defined as a kernel instance, but doesn't have anything that's different than a regular instance, except things like it has no devices, no file systems. It's all it does is just be completely blind. InstPS is just an extension. It's just an extension of regular PS. And let's show the -I flag to InstPS. This is just like PS, shows the zeroth instance, which is the kernel instance. As you can see in there, we have the swapper and the Zen stuff and page daemon and instant daemon and all sorts of things that are completely separate to us. So for example, if I run it for the first instance, which is us, I see the same thing as I get with this. So now we're doing this in the same. And start up. What's the name? So mount. So there's another device, which is just another hard disk. The user interface for this has been pointed out by several people to be very ugly, and it's true. I apologize, I'm a pretty bad user. So now I'm going to boot an instance off of this device right here. So I just, sorry, a little bit delayed message right here, but here's where it automatically detects the file systems on the device, and basically does all that logic that we have right now in the VFS mount root over things like the root device and the root dev num, or done per instance. So now it's running. Now, I still can't see it, so everything continues here as normal. So in my instance, everything is perfectly fine. But as we can see with this handy insinfo command, there are now 2 instances, well 3 technically. There's a roots instance, UID number 0, and then there are 2 other ones. One off of XPD0A, which is one I'm running right now, and one off of XPD1A. NetBSD 3.1 BSD will be a NetBSD guest. So if we peer into this, I see it's got syslog D, SSHD, inetd, and cron. Instanit is just my hacked up init. So the best part is when we log into it, because it has SSHD running. As I said earlier, the network has not been appropriated. Please don't crash. Very nice. Okay, so now I've logged into the other instance. That was a lot like logging into another computer. As you can see, we have the same kernel information right there, but a different host name. In fact, everything is different. SSHD wasn't running in the other instance. I was running this right here because I'm in a different place. Yeah, that's pretty much it. We can have overlap with PIDs. As you can see, there's a PID one for this and the other one, obviously being in it. We can have the same user IDs. So all that can be the same because it's not overlapping. As we went over earlier, the actual data structures in the kernel are completely separate. But now I'm going to do something fancy. I'm going to kind of cross my fingers because I don't want to see that. Instance T kills an instance. So I'm going to try to kill, and all it does is send a signal to init. So I'm going to try to batter the instance I'm running in right now, which is connected to a console. And have to wait a little while since it's got the timeout. So basically what I want to do is make this jump down into single user mode. And we can have one instance in single user mode completely not affect other instances. Bingo. So there we are. Now the instance, the first one that I started, is in single user mode. As you can see, all I have is init, and that's it, and the shell is running it. Now if I exit out of this and go back into multi-user mode, those are fine, by the way, they're little things. As you can see, I'm running in that first instance right there. All the other ones are still running. So I was just in the first instance and brought it down to single user mode, brought it back into multi-user mode, and none of the other instances were affected. So they're completely fine. So that SSH is still running, has always been running. It's completely unaffected by the fact that I was dropping down to the console. Very nice. So let's kill all this stuff, shall we? So now instantial T is going to kill the other instance, terminate. So I'm going to kill terminate number 2. Of course, we have to give it a few minutes. As we can see now that everybody's entered into the exiting mode. There we go. So the mounted device in there was unmounted. By the way, all the mount lists are different, so if I would have run mount, I did. Earlier, if I run mount in one instance, I see a completely separate thing. And it's not being FreeBSD'd, which is just like an editing list. It's actually a different mount list. Right, so now I only have 2 instances being the default on this. So I'm going to bail out of this completely. Alt still exits the whole system. And that'll confuse. All right, not back to 10. So that was it. We just saw molts running in NetBSD. Then a Molt 10 instance was started, which is a paravirtualized forked NetBSD 3.1 code. We had multiple user lamps inside of it, so we were able to log into them, dropping one down into single user mode, having the other still being in multi-user mode, everybody was still happy. So, any questions? Yes?
Given the value you're placing on complete isolation,
Yes.
how do you address the problem with the cache as a covert channel and you can't get around?
Well, the isolation is only from what the instance can see. So if an instance can actually see into something and manipulate it directly from a task, then that is a resource that I'm concerned with. For example, take something like the vnode cache. Right? We don't really interact with that. That's done in BFS. So there are obviously things we can do in syscontrol to play with it, but we can't really affect it in a meaningful fashion. So there's really no need to appropriate the entire vnode cache into instances because why? We don't see it. If we see it, then we have to appropriate it. If we don't see it, we don't have to. There's a very determinable line between what is seen and what is not seen. So that's not an unreasonable limitation. There are some areas that are very complex, especially things like caches and the VFS, but those complexities can all be worked out, it just takes time. So again, when I talk about resources, the critical thing to mention there, and I was a little bit hand-wavy on this, is visible resources from the task. So that which we can immediately manipulate and see as a kernel service is a resource. Everything else is basically in a different tier of the kernel. So I'm concerned with the very top half of the kernel services, not the bottom half. So not obviously not the bottom half, but even the mid half. Things like raw caches, memory pools. There's no need to appropriate them because they don't have a context associated with them. Things that have a potential context need to be appropriated. Things that don't. That was kind of a general question and a general answer. If you have specific things inside of the kernel that you want to point out, then we can talk about that one by one. But that's kind of a general answer. Is that what you're seeing must be appropriated? It may not be easy. In fact, a lot of it was very hard. But it can be done. It just takes time and care, like raising a puppy. Any other questions?
Excuse me.
Yeah.
Time is over.
Yes.
Please,
It's
ask
over.
us.